Hello, I'm Srirangan Sudarshan and this is my recording for Lab 3. In this lab, we hope to use the principle of energy conservation and current conservation to predict the behavior of circuits as well as simulate these circuits and analyze their behaviors for different combinations of capacitors and resistors. We see that the current value and the voltage value matches up with the predictions. Similarly, we see that in an RC circuit, the current and the voltage depend exponentially upon time, as given in the equation delta V is equal to delta V naught into e to the power negative t divided by RC, where t is the time and delta V is the potential. We use Kirchhoff's law, where the node rule states that the current entering a node is the current exiting the node, as well as the loop rule, which states that the round trip potential is 0. We use the concept of Ohm's law, where V is equal to IR, the concept of steady state circuit and combinations of resistors and capacitors in series and parallel. We also use the concept of capacitance, where C is equal to Q divided by V, where Q is the charge and V is the voltage, as well as C is equal to epsilon naught A divided by D, where A is the area and D is the distance. We see that the time dependence of the resistance capacitor circuit follows the equation that we discussed earlier. In the first model, we use two different resistors of 47 ohms and 100 ohms connected in series, as well as two batteries of 1.5 volts each. We assume that there is no resistance from the ammeters or the wires. In this simulation, we are able to see that the current value is 0.02 amperes. We are also able to predict using the Ohm's law equation, and we get the value of current to be 0.02 amperes. Thus, the current reading from the prediction matches up with the values from the actual simulation. We are also able to see that removing an ammeter and replacing it with the voltmeter reads a value of 0.0 in the ammeter, as there is no current flowing through the circuit. Also, since it's an open circuit, the only potential is the potential of the battery, and hence the voltmeter reads 3 volts. Reversing the ammeter reads the value of 0.02 amps again in the closed circuit. If we were to calculate the round trip potential, we see that B to A has 3 volts, D to C has negative 0.96 volts, and F to E has negative 2.04 volts. Thus, the round trip potential is 0 volts, which aligns with the loop rule. We also see that the voltmeter has very high resistance, and hence the current reading still remains the same, as it does not affect, the presence of the voltmeter does not affect the circuit. We are also able to plot the graph, and we see that this is the graph that we plotted. Next, if we were to connect one of the ammeters in parallel with the 100 ohm resistor, we are able to see that the current reading increased to 0.06 amps as the resistance of the portion of the circuit decreases. The resistance over the 47 ohm resistor is 48 ohms, and over the 100 ohm resistor is 102 ohms. In the second model, we use a 0.2 Faraday capacitor along with a bulb and 9 volt battery. Initially the bulb glows, but then it stops glowing after the capacitor is charged. Then if we connect the bulb only to the charged capacitor, it glows again till the capacitor is completely discharged. The 10 ohm bulb takes 10.3 seconds for charging and 11.7 seconds for discharging. The 20 ohm bulb takes 16.8 seconds for charging and 21.9 seconds for discharging. If we plot the values of the natural logarithm of V divided by V naught over time, we see that we get a linear graph, and the straight line has an equation with a slope of negative 0.166. Using this, if we were to calculate the value of the RC, which is negative 1 by slope, we get the value of 6.101 seconds. This matches up with the value for the expected value of RC, which is 30 ohms into 0.2 Faraday, which is 6 seconds. There should be no errors in this model, as it is an ideal circuit. However, some errors could be due to human factors such as incorrect readings, etc. If we were to use the real-life ammeter instead of an ideal ammeter, the real-life ammeter has some amount of resistance. This means the current would therefore be lower as per Ohm's law. If we were to use a real-life capacitor, real-life battery, and no resistor in a circuit, then the circuit will still not immediately charge up the capacitor. Instead, the capacitor would take up some time, as the wire materials have some amount of resistance. However, the ideal simulation predicts that it glows up the capacitor charges up immediately, which is wrong. And conclusions, we are able to see that the node rule and the loop rule hold true, and that in an RC circuit, the voltage depends on the time exponentially, and we are able to plot it. Thank you.